Yeah, thank you so much for everyone attending today. So yeah, my name is Akali Asai, and I'm a PhD student at University of Washington. And today I'd like to talk about our recent papers about like adaptive and like trustworthy NLP with retrieval for like information access for everyone. Oops. Okay. Yeah, like so large language models have shown like promising performance across like many different tasks, even in like zero shot. Like this recent paper shows the like benchmark like GPT-3, ChatGPT, as well as like fully fine-tuned models. And they found that like in some tasks, like prompted ChatGPT is actually like outperforming like fully fine-tuned models. Motivated by such great success on like academic benchmarks, now like those large language models integrated into like real world systems. In particular, like recently, like multiple large language model based search systems, such as Bing Chat or like U.com, got like really popular. And those systems, given a user's query, search, document, and summarize that result, and returns a responses so that like users don't need to search and read web documents by themselves. Like although those large language model-based knowledge interface makes information more accessible to billions of users, there are like many challenges we have to like address. So first, like large language models hallucinate or like make factually incorrect responses a lot, even like given retrieved documents. Here, like I prompt explain Akali Asai, and ChatGPT generates some like convincing and fluent response. It started with like Akali Asai is a researcher in the area of NLP and like machine learning, which is correct. However, like from the second sentence, it started hallucinating. Like for example, like I'm not a research scientist at Google Tokyo or like adjunct professor at the University of Tokyo. The issue is that the language model output now looks like plausible and also long. So it's really hard to verify if it's true or not when we don't have access to external systems or knowledge. Also, large language models knowledge can get obsolete pretty quickly, as they are often trained on large web corpora collected at certain timestamp. For example, a Japanese prime minister changed in 2021, and if I ask who is a PM of Japan to ChatGPT or like GPT-3, both of them answered incorrectly. Although ChatGPT is slightly better, as it acknowledges the world knowledge might not be updated. This indicates that like we have to continuously train those like language models to keep up with the current world. Lastly, many papers show that like those memorizations only appear in like large language models. If we try to build a language model that can memorize a lot of factor knowledge, we have to scale the model size to like hundreds of billions of parameters, which is like almost prohibitive for like most of the companies or like academic groups. I think all of the core issues are essentially like coming from the limitation of trying to memorize everything in the language models parameters. We train large language models on a bunch of pre-training corpora, and then at test time, we query language model, hoping that like it can locate and retrieve the certain knowledge from the billions of parameters. In other words, like their parametric knowledge or like memories. I'm quite interested in whether it's possible to leverage external knowledge, external non-parametric memories, instead of trying to memorize everything in their own parameters, as we humans do in our daily life. Like in our daily life, whenever like we are not sure about like something, we go to the web or like read books instead of trying to like really hard to remember something we learned 10 years ago. I think this should be like effective for like NLP model development, and effectively incorporating parametric and non-parametric memories helps us to overcome the issue of like staleness, hallucination, or like parameter efficiency. For example, like here, instead of trying to just like directly answer this question without any external knowledge, we can like use a retrieval system and to find like a document which explicitly says that like Fumio Kishida is a current prime minister of Japan. And then like we can feed this document along with the original query. Now like it's super easy to like answer this question because like the model can just like look at and like extract the answer from the document. So I've been working on efficient and trustworthy NLP systems with retrieval to make information more accessible for everyone. In particular, we develop NLP systems based on like large language models with retrieval module. which helps us to effectively recode and use the non-parametric memories. There are two key components of retrieval-augmented language model. First, given an input, a retrieval system finds related non-parametric memories or web document. For example, here, given a question, we find a document explicitly mentions that like this person is the Prime Minister of Japan. Then like we incorporate these retrieval narratives, and these narratives will be fed into the generation component large language model with the original input. Today, I will talk about 3 of my papers to understand and develop retrieval-augmented language models effectively. First, I will talk about our analysis paper that analyzes the effectiveness and limitation of the parametric and non-parametric memories when it comes to like factual narrative memorization, such as like who is the president of the United States. We found that retrieval-augmented language models, we found that like language models, even like if we scale the models to like hundreds of billions of parameters, cannot like memorize well like long tail factual narratives, while like retrieval-augmented language models can be quite effective in like such long tail distribution. On the other hand, current retrieval system can also like struggle in like some domains, motivating us to develop more general purpose retrieval system. So in the second part of my talk, I will talk about our paper to develop general purpose retrieval system by improving their training with like instruction tuning. Lastly, even if we have a decent retrieval system, the current language models aren't explicitly trained to focus and generate based on the correct evidence, correct like web document or like non-parametric memories. This results in like models over reliance on like spurious evidence or like hallucination. So we introduce a new architecture and training method to train a large language model to make it to train the large language model to focus on like more like reliable evidence. I will conclude this talk with like some of our earlier work applying retrieval-augmented systems to multilingual information access, which is like even more challenging. And also like I will talk about some like remaining challenges and interesting future application of retrieval-augmented language models. Excuse me. Now let's move on to the first section. Also, like many of the NLP papers claims that like language models hallucinate a lot, and augmenting language models with retrieval helps to mitigate those issues. Little work actually quantified and tried to understand like when language models and how like retrieval augmentation, when language models fail, and like how retrieval augmentation helps to overcome such shortcomings of like language models parametric narratives. So in this work, we conduct a large-scale analysis on like language models memorizations and effectiveness of like retrieval augmentation in long tail. So before talking about the details of this paper, I'd like to like briefly recap like some of the recent work investigating language models memorization with a focus on like factual narrative memorization. So there's a growing number of evidence that shows that like pre-trained language models can actually memorize a lot of word narratives in their own parameters. In 2019, the famous like llama paper shows that like pre-trained BERT model can correctly answer knowledge-based questions. Oh, by the way, like this talk is like originally like created for like NLP like researcher like engineers. So there might be like some like details about like NLP specific details. So if you have any questions, please like feel free to ask like after this talk. And also like in 2020, the T5, there's like a new famous T5 paper, which basically like train a single model to like conduct like many different like tasks from like machine translation, summarization, and so on. And the same authors introduced a task called a closebook QA, where like given a question, the model needs to like generate answer directly without like retrieving like any document. And they show that like when they increase the model scale, actually like those large language model-based systems can memorize answer and like output the correct answers to the question. And although like this T5-based method actually like fine-tuned on like specific data set, the original GPT-3 paper actually shows that like even without fine-tuning, the model can achieve like really high performance on like one of the most famous like open accurate data set, outperforming like one of the state-of-the-art retrieval augmented system. Well, like most recently, some papers even shows that like we can retrieve parametric memories by prompting them. So like we basically like prompt like language model saying like, oh, please generate evidence to answer this question. And then like we use the generated document, like generated from like large language model to like answer like open domain question, which some people call like generative retrieval. So those papers shows that like language model can actually memorize a lot. But on the other hand, as I mentioned, like GPT-C or like ChatGPT still like hallucinate. So like when and why like language models like fail to memorize. So for example, like if we ask question like who is Barack Obama, then like the model's output is like 100% correct. Well, like if I ask question about another US politician, then like the answer is incorrect. So like to understand like when those language models outputs are not reliable, it's quite important to build trustworthy NLP system. So in this work, we conduct a large-scale analysis to answer those like interesting research questions about memorization in like large language models and like how to use like non-parametric memories effectively. Our analysis focuses on like factor analysis, which is defined as in this like narrative triple format consisting of subject, relationship type, and object. And we assume that like a model memorizes narrates if it can correctly generate the target object given the subject and relationship. And we formulate this as an open domain QA task where we convert original narrative triples into natural language questions. And like the model needed to like answer this question. This work focuses on like two important dimensions of like factor analysis, which have not been considered in prior analysis of factor analysis memorization. First, we use subject entity popularity, which is defined as Wikipedia monthly page view. Our hypothesis is that factor knowledge about popular entities can be more easily memorized by like factor knowledge than like factor knowledge about like less popular entities. Another aspect is like relationship type. Even about the same subject entity, knowledge about like certain aspect can be like more easily memorized by other aspect. For example, like answering the like famous professional soccer players like sports is like quite easy, while like answering his parent might be like more challenging. Also, like during our pilot studies, we found that like most of the existing like open domain QA datasets often like only discuss like the popular entities, which can result in like overestimation of models like memorizations. For example, like there's a pretty like famous open domain QA dataset called like natural questions, and like which is basically like collected many, which is basically constructed by like collecting many like Google search queries and then like annotates the answer as by like hiring like many like annotators. And in this dataset, as the questions originate from like Google search, people are like mostly talking about like the popular entities such as like Joe Biden. And so like when we are looking at the like popularity of like subject entities in like natural questions, then we found that like most of the questions are about entities with like thousands or like millions of like page views, which only like account for like a few percent of like Wikipedia. Here, like we compare like the popularity distribution with another open domain QA dataset, which is called like entity questions, presented as like this like green bars. And you can see, as you can see, like this entity questions has a like huge like spike on the left side. We found that like to understand models memorizations, having a data set covering like diverse distributions, as well as like fine-grained subject and relationship type annotation is necessary. So in this work, we actually construct a new data set called PopQA, which first samples knowledge triple from like Wikidata, which is like one of the biggest knowledge base in like in the world right now. And we convert knowledge triples into like natural language questions and then like collect the popularity information using like Wikipedia API. So now I would like to move on to the like interesting finding from this paper. So first, we actually like found that like so language models, like especially like GPT-3, O3 or O2, which is kind of like a predecessor of like ChatGPT, actually like memorize a lot. So here I show the like models performance models like aggregated performance as well as like the power relationship type performance, and like the y-axis is accuracy. And as you can see, like the overall, the GPT-3 models actually like achieve like almost like 40% accuracy. And also like in some relationship type, the model performance is like quite high. And as you can see, like as the model scale increase, actually like the performance also like improves a lot. We found that like there is like a really strong correlation between like accuracy and popularity. So like here, like the y-axis is a correlation between like popularity and accuracy. And as you can see, like first, like across different relationship types, there is like positive correlation between like popularity and accuracy, which means that like more popular entities, questions about more popular entities can be memorized much better than like less popular entities, which like demonstrating that our initial hypothesis is actually correct. Also, like as you can see, like as the model scale increases, actually like the correlation is like gets like stronger and stronger, which means like the larger models memorize a lot, and like this memorization is basically depending on like how popular the topics are. Also, like this is kind of consistent with some findings from prior work that like larger models memorize more, and so like scaling actually helps. However, when we take a closer look at the result, we found something really interesting. So in particular, we found that like scaling helps language model memorization for like popular factual knowledge. Well, like it doesn't help for like long tail knowledge. For example, like knowledge about like really kind of niche topic. For example, like here, the red lines shows the like model's performance on like questions about popular subjects such as like who is the president of the United States. And for those cases, actually, like, as you can see, like when we scale the model size from like 1.3 billion to 175 billion, we can see like clear like upward trajectory as an upward trajectory of performance. However, for the like when it comes to like less popular subject, the model performance actually like the model performance presented as like blue or green line here actually like almost like remain low, even like scaling up model size from like 1.3 billion to 175 billion. We argue that like prior work often uses like really popular like benchmarks that are like really biased towards like popular subject, as we discussed in earlier this section. And so like we argue that like the finding from prior work may like influence the effectiveness of like scaling when it comes to like factual knowledge memorization. So if the scaling doesn't help us to like improve like language models memorization for like long tail, can like non-parametric, one of the question is like, can non-parametric memories like retrievable document alleviate this issue? So here we try a simple like retrieval then retrieve read approach, and like we evaluate this like retrieval-augmented language models on the same data set using like the same like base language model without any training. So like this simple approach basically like first retrieve document and use the top one document from retriever as a part of prompting. So like before, like in the prior section, our baseline model only used this like question, who is a prime minister of Japan. But like now we prepare the like retrievable document, which is just like top one paragraph from Wikipedia. And like we feed those questions on the context together into like large language model. So like we don't need to like train model at all. We just like prompt. But this approach actually like really strong and gives us large performance improvement. We have seen like huge performance improvement on like our data set as well as like entity questions across different models. And especially like smaller model get like larger performance improvement. And in particular, like with retrieval, 1.5 billion GPT-Neo with can like even beat the vanilla GPT-3, demonstrating that like incorporating non-parametric memories from the web can give us huge performance improvement and enables to be like way smaller and efficient language model based systems. More and more recent papers actually like confirm this trend and across like different knowledge intensive tasks. But like why retrieval is that effective? To answer this question, we checked the relationship between like models accuracy and popularity. We found that like retrieval augmented systems are often stronger than like language models without retrieval in like long tail. So like here, like I highlight the model's performance. I highlight the relationship between like the popularity in like x-axis and like accuracy in like y-axis, and like the areas in like blue rectangle shows like the less popular entity questions. And as you can see, like here, BM25 contributor, which is like using like retrieval-augmented language models, outperforms like the vanilla language models or like another models using like parametric retriever by large margin, which is good. But also like we had some like quite interesting finding that like such like vanilla language models are actually like really performing well, or like even outperforming like retrieval-augmented language models in popular factual knowledge. Here, like I highlight the questions about like really popular entities. And as you can see, like the orange or like bluebirds, which are like using like the just like language models to generate answer, outperform like BM25 contributor. So we found that like there are like many cases where like a vanilla language model actually answers correctly, which means like the model is actually like memorize answer. But like when we combine like retrieval system, it started like answering incorrectly due to the incorrect retrieval context. So here like the question is like who was the director of like blog, and the correct answer is like Sanjay, and like the regional language model actually like answer correctly to this question. However, like when we use like retrieved context, the retrieval language model actually like answer incorrectly because like this retrieval context is actually like not related to the question. This context is like talking about American film director whose name is Noel Block. As this paragraph has like a lot of lexical overlap to the question, this person is the director of this movie. So like, but this paragraph is kind of confusing. So like the language model extracts the answer from this paragraph. Even the current best retrieval system is not perfect, and sometimes they retrieve incorrect evidence. But existing language models aren't really trained to ignore such incorrect evidence. And so like when retrieval errors happen, it can like be easily distracted, even the model already like memorized answer. So like we tried to see like if it's possible to build a more like effective retrieval-augmented language model that can like effectively like incorporate the parametric memories with when it's necessary to get the best of the both world. So in this work, we propose a really simple pipeline method, adaptive retriever, which only retrieves when the subject entity is less popular. So we find the like popularity threshold. We find the popularity threshold on the development set, and at the test time, we use retrieval if the subject entity is less popular. But otherwise, like we just use standard language model. So for example, like if the question is like who is president of the United States, then like we just use language model. Well, like if the question is asking about like what is the like first artwork of like this Japanese comic artist or something, then like we use retrieval to find the like reliable evidence. And this actually gives us large performance improvement on like stronger language models. As like they've already like memorized a lot to avoid memorize a lot. So like avoiding unnecessary knowledge retrieval actually like gives us like huge performance improvement. And also it improves like efficiency because like now we don't need it to like retrieve, and also like we needed to like feed the long context to like large language model, so we can reduce the like inference time, latency, as well as like API cost to like GPTC. So the takeaway is like scaling like may not be like helpful to memorize like long tail knowledge, but like retrieval augmentation or like incorporating non-parametric memories can be like really like effective, especially in like long tail. And we found that like a simple like adaptive retrieval method performs well in like question answering task. And we believe that this is a really promising direction to build like more efficient and also like effective retrieval augmented language models. And so like so far, like we found that like to build a reliable retrieval augmented language model, having a general purpose like good retrieval system is a key. And in this section, I will talk about our paper introducing instruction tuning for retrieval to build a single general purpose adaptable retrieval system. So yeah, like finding the right evidence, like or like non-parametric memories is a key to build a successful retrieval augmented language models. So here, like given this like input query, our retriever must find the green document, which is like actually answering the questions, instead of being like retrieving like other documents, talking about like other countries' PM or like political parties. And historically in like NLP, we have been like using like keyword matching based retrieval systems such as BM25, which basically like build a huge like matrix of like keyword and then like find the documents based on like such data sparse, such data sparse embeddings. Recently, like we have seen like success of the neural pre-trained encoder-based retrieval system. Most of them are like based on like really like efficient like BART-based encoders. Those retrieval systems basically like fine-tune like pre-trained encoders such as like BART on like large amount of like a pair of documents and like the input queries, and like they train the model, they train the encoder-only model using contrastive learning. And at inference time, it encodes question and passages using these like trained encoders. And to find the documents, we just simply compute the like similarity of embeddings of like question and also documents. And those systems have outperformed the like term-based or the keyword-based retrieval system by large margin when a bunch of training data is available. For example, like dense passage retriever, DPL, which is one of the most widely used neural passage retrieval system, has obtained like 20% absolute performance gain from like BM25 when trained with like 60,000 examples. However, like in most of the domains, we don't have like that many training data. And like, so like we have to like build a retrieval system by like maybe like training them like on the small amount of data, or like just directly transfer the training system to like new domain without any training. But we found that like those neural retrieval systems actually like struggle a lot when it comes to like zero-shot transfer or like out of domain. So there's a widely used zero-shot retrieval evaluation dataset called BEER, and on BEER, such neural retrieval systems performance poorly compared to BM25. Also, like this means that like those models cannot be like transferred to like new tasks whose input may not be like similar to the original training data. At the same time, like in the large language model community, we have seen the great success of instruction tuning. So instruction tuning is a really straightforward, simple idea where like we train a single like large models on like many different tasks with instructions. So instructions basically describe the task and like what is the like expected input and output. And once we train the model with instruction on like many data sets, some recent papers shows that like those like instruction tuned language models can actually generate pretty well to like unseen tasks without like any parameter update. And also like those instruction tuned models can like return the like output that are like better aligned with the user's actual intent. And we believe that this is actually a pretty like good way to like incorporate like our to address the issues we have in information retrieval. In information retrieval, historically, like we tried to build separate task-specific systems for like different end goal. For example, like if we want to build a system that can like do like code search, and like we try to like collect data from like GitHub or like some like code text to code data set, and then I try and separate it into a system. But those like training a separate retrieval system for each different intent has like many different issues. First of all, like even if we have the same query, the intent behind the query can be diverse. For example, like if the user input is like implementing batch normalization in Python, user may want to find like Python implementation or like similar questions or like even like answer. And those implicit user intents are like usually like not like explicitly like included in like any of the input data. And we try to like build a separate system to model such implicit intent by collecting many input and collecting like many like positive and negative pairs. But as I mentioned, like it's really hard to like collect such many examples to be like separate systems. And also like simply like having like separate systems for like different intent can be like can make the like inference pipelines more complicated. And also, as I mentioned, like even with the same query, the intents can be diverse. So in this work, we conduct the first study of like instruction tuning for retrieval to overcome such like zero-shot generalization, as well as like alignment to like diverse user intents. In particular, we formulate a new task, which is called like retrieval with instruction, to model users' intent better. And then like we construct a large-scale retrieval dataset consisting of like 40 NLP tasks with instructions. And then like we train a single retrieval system called Cloud on like these like large data set. So we first formulate a task retrieval with instruction. Here, like I shows a like normal retrieval task on the left side and like our retrieval with instruction on the right side. As you can see, like for normal retrieval task, given the query, we build as like separate retrieval system and like which has access to the specific target document and retrieves the like expected target document. While here, like we feed the like both query as well as the intent, as well as the instruction that defines the like intent behind the query. And we try to build a single retrieval system that can incorporate such instruction and also like has access to like many different documents from diverse domains and return the documents that actually like align users' instruction and also like related to the input query. So for instance, given an instruction, I want to find Python code, our system, our single like task-aware retrieval system returns Python code. If the instruction is like, I want to find Python code, well, like it find like answer from like Stack Exchange. If the intent is like, please find answers for me. One important thing is that the current instruction tuning datasets usually like exclude retrieval tasks because the format is kind of different from like standard like language model centric task. And it's kind of open question like how we should like define like instructions for like retrieval task. So in this work, we annotate diverse instructions for like new like 40 new dataset, but we also like try to like include like 3 key components defining a retrieval task when it comes to instruction annotation. First, like the intent defines the like end goal of retrieval, such as like answering this question, and domain describes the target domains, and like unit describes the expected retrieval units. For instance, if an expert user want to like do scientific fact checking, they may want to find a sentence from a scientific paper abstract. Well, like if a non-expert user wants to know like if the medical claim is actually true or not, then like they might want to find easy to understand like website. So to conduct instruction tuning for retrieval, we construct a large-scale dataset with instruction called Berry. So this one consists of like 37 dataset from like diverse domains, and we annotate the instructions following the schema I just described. One key point here is that to cover diverse domains, we actually collect and convert non-retrieval datasets such as summarization into retrieval tasks. The details of like how we actually construct this dataset is in our paper. Built upon this dataset, we trained the first instruction following retrieval systems called Cloud. We tried 2 different architecture. The first one is like following standard dual bi-encoder dense passive retrieval system, and we encode like instruction and question together, and we compute the similarity of like instruction guided question representations and like documents representations. Another baseline is like more powerful but expensive Tau tool, which first sample like top documents using an efficient retrieval system and then like rerank the output. This model jointly like encode question and document using a like big language model, enabling rich interaction between a query and document. We prepare the instruction to the query, and so like now this language model is needed to judge if the document is actually related or not, given this instruction. And once we encode and like predict the probability of a document is like related to the question or not, we derank the documents based on the score. I will not talk about the details of the training, but like those 2 models are trained with contrastive learning using like positive and negative samples available in our dataset. And please check out the details in our paper if you're interested in. And in this work, we investigated models performance on like zero-shot retrieval as well as like open task, open domain retrieval, or like cross task, cross domain retrieval, where all of the domains and tasks are pooled. For zero-shot retrieval, we use like, why do we use why do you use like beer and like load the benchmark? And for closed task and cross-domain retrieval, we construct our own evaluation suite. And our experiment shows that like on both of the setup, our tout will significantly outperform like other models with more parameters, indicating the effectiveness of like instruction training for retrieval. We also found that like removing instructions at training time or like test time result in performance deteriorations, further demonstrating the effectiveness of instructions. In summary, we try to like shift the like classical like IO paradigm from multiple task-specific models to a single unified model that can like be instructed at test time. And we construct a large-scale dataset with instructions for instruction tuning for retrieval and build a single like task-aware retrieval system that user can instruct. And we achieve like strong zero-shot and open domain retrieval performance. So far, like I've been talking about like the effectiveness of retrieval-augmented systems and like how to build a generalizable retrieval system. However, like one natural question is like, can we also like improve a language model itself to better incorporate non-parametric memories? So the current best systems, such as like even like Bing Chat, can still like hallucinate a lot. Even like when we have like the right evidence. Like more and more examples have been found by users where like Bing QA actually like cites the right evidence, but still like generate incorrect result. So like why does this happen? One explanation of this phenomena is knowledge conflict between non-parametric and parametric memories, or like conflict among like non-parametric memories. As the large language model itself memorizes a lot, sometimes like the language models prioritize their own parametric memories over non-parametric retrieval document. Here, we asked the question like which country won the most medals in like Winter Olympics, and like during pre-training time, the answer was like the US. Well, like those information needed to be like updated, and like after like the document shows that like right now like the Norway has like the most gold medals. But as the model has like really strong grip on their own parametric knowledge, sometimes the model prioritizes like their parametric knowledge, even though like the correct non-parametric knowledge is provided. Or like even among non-parametric memories, there can be like some inconsistencies. Here, like one of the article is not up to date, resulting in like inconsistent answers, Norway and Germany. So we argue that like this happens because like the models during training time, the model is not like retrained to like focus on the right evidence. It should like generate answer on. So in the common approach to train such like fine-tune such like language model-based system, we don't have like much control about like what a language model can focus during generation. Like during training time, we just like input like question and like passages, and then like a model generates token probability for output sequence Y, given the input query, given those input. And we train the model so that it can maximize the probability of generating the gold answer Y hat. Therefore, during training time, the model is not explicitly trained to judge which evidence it should actually look at. Here, like even though like those two paragraphs include the answer string 7, only the green one provides sufficient information to answer, while the second one, like even the second one has the answer string, but it doesn't actually answer this question. So in this work, we studied the problem of predicting evidentiality to make it generate based on reliable evidence. Evidentiality positive passages include sufficient information to answer the input query, while like evidentiality negative passages don't. And the goal here is like to make the model to focus on like these positive passages instead of being distracted by the red passages. So our model jointly like learns to generate answers as well as predict evidentiality for all of the non-parametric document evidence. There are two major challenges here. The first one is like how to build such system. Before talking about the architecture detail of our evidentiality guided generator, I would like to talk about how standard encoder decoder language model works. So here, like we first encode input and also the retrieved documents. Then like we feed the summary representation of encoded documents and also question into decoder. model will be trained based on the close entropy loss between like the generated token distribution y and like the correct goal token distribution y hat. Our Evidentiality guided generator shares a single encoder and has two separate decoders, one of which is for answer generation and the other one is for like evidentiality predictions. Here, the first P1 is positive paragraph, while like the P2 is a negative paragraph. So this predictor predicts the positive and negative respectively. We then train a model with a multitask objective of generation and like evidentiality classification laws. Another challenge is that most of the data sets lack annotation for like which non-parametric memories or documents provide sufficient evidence to answer. And also like evidentiality can be like model dependent. I will skip the details here, but in this work, instead of like using like some string matching, we use another model's prediction to level evidentiality on all of the passages. And this approach is not task dependent. So like we can apply the same approach for like diverse knowledge intensive NLP task. And actually like we evaluate our model on like 3 different tasks, open domain QA, fact checking, or like knowledge grounded dialogue. As you can see, like input output of those 3 tasks are completely different, but all of them require some kind of external knowledge to make a correct output. And we found that like our method achieves like stronger performance on like all of 3 tasks and like 5 data set. So the takeaway here is like the current language models are not explicitly trained to like use retrievable documents, and they cannot like effectively like incorporate, judge, and incorporate non-parametric memories. So like we introduced evidentiality guided generator to make language model to focus on like more reliable evidence. And we show the effectiveness on like diverse knowledge intensive tasks, including QA, dialogue, and fact verification. Now I would like to briefly summarize today's talk and also like some interesting future direction. And so today I talked about like 3 of my papers on like analyzing and developing effectiveness of like analyzing and developing effective retrieval-augmented generation system. So we found that like incorporating non-parametric memories can be like super effective, especially if we want to build a efficient like smaller language model based system. And also like we found that like better like training strategy can help us to build a more generalizable retrieval system. And also like we found that like it's actually important to like come up with like better training or like architecture to enforce the model to pay more attention to like reliable evidence. I will not talk the details, but we've been also working on such retrieval-guided NLP systems for more challenging setups, such as multilingual information access. In many languages, we don't have sufficient information on the web, unlike English. And when a question is asked in like target language models may not be able to precisely map and recode the knowledge expressed in different languages. So we carefully train multilingual semantic search retrieval system and also like multilingual generation model that can incorporate non-parametric memories expressed in like many different languages. This enables users who speak like who don't speak like one of the top major languages can like still like access like information they need. And I would like to conclude the talk with like some of the interesting open questions in retrieval-augmented language models. First, as I discussed in the first section, the current language models indeed memorize a lot. And adaptively combining non-parametric memories is quite important to build a general purpose retrieval-augmented language model under like certain resource constraint. Second, the language models output can be like still not 100% trustworthy. Having a better control to make them grounded to some external evidence or like making it easier to verify is also quite important. Also, like some recent papers shows that like some like recent systems such as like Bing Chat provides like some external links. Usually like it's really hard to like actually verify because like the link has like leads to like the website, which has like multiple pages. So like we needed to work on like how to build retrieval-augmented NLP system, which enables users to like easily verify the like evidence. Lastly, more and more interesting applications come up in the area of retrieval-augmented language models. For example, like this year's iClear has like 2 spotlight paper about like retrieval-augmented generation for code generation, or like retrieval-augmented generation for like molecule generation. And I think building retrieval-augmented systems for like such expert domains would be really exciting as well as like important, because existing language models often struggle in like such long tail areas. Okay, so thank you so much for listening to my talk today. And if you have any questions, please feel free to contact me or like ask questions